Okay, so in this video we are going to again look at the concept of rolling without slipping and the transition from rolling without slipping to slipping, but in this case the motion is going to be a little bit different than the prior videos, or the motion generation is going to be a little bit different than the prior videos. So in this example we will consider the case of a wheel on a horizontal surface. Moving horizontally under the influence of gravity, but here the motion is being generated by a internal torque that is being provided, and so C is the center, M is the mass of the wheel, and this is the direction of positive theta and theta dot, and this is the direction of positive x dot, etc. So also the coefficient of friction between the wheel and the horizontal surface is mu. Now in this problem what we want to do is we want to find out at what torque this wheel is going to slip on the surface. Now this problem, analysis of this problem is similar to the analysis of a wheel of a vehicle, let's say of a car. So in a car the engine produces the power, and the power is essentially transmitted to the four wheels through the transmission. To be specific, the engine produces a torque and it is transmitted to the four wheels, and what happens is that that torque causes the wheel to actually push back on the ground, and the ground in turn provides a equal and opposite reaction force, and it is that reaction force that causes the car to move forward as a whole. So that is how we analyze the motion of a wheel, and so you can motion of a wheel where there is an internal torque. So you can consider this single wheel to be one wheel of a vehicle, and the torque is getting is being transmitted to this wheel. So the question then is find the maximum torque when the wheel starts slipping. So the maximum torque at which the wheel will start slipping is the question. All right. So let us draw the free body diagram of the wheel. So we have the torque. This is our x-axis. This is the angle theta. There is of course gravitational force passing through the center. Let's say that the instantaneous point of contact with the ground, let's denote that by P. let's say that the normal reaction is N. This is the normal reaction due to the contact between the wheel and the ground. Now in this case, the torque is trying to push the wheel at the point of contact. It's trying to push the wheel back, and it's relying on the ground to give a forward going push to move forward, and that push that is coming from the ground is actually the friction force. So in this case, the friction force is this way. So the friction force in this case is the force that causes the wheel to move forward. Right? So this is the set of forces, and let's say that the radius of this wheel is R. So I forgot to mention that here. So the radius is R. And we'll consider the wheel to be a disk. So the equations of motions are going to be mx double dot is equal to the summation of all forces in the forward going direction, and that is F. In the y direction, that is in the vertical direction, we will have mg is equal to n. So we have an expression for the normal reaction, and the rotational equation is going to be IC theta double dot. IC is the moment of inertia of the wheel relative to its center of mass, is equal to the summation of torques and moments. So we see that T is a positive torque because it is causing, or its direction is such that it tends to accelerate theta, whereas the force F is providing a negative torque in the amount of F times R, because the force F is trying to decelerate theta. Now there are two ways to solve this problem. One is to assume that the wheel is rolling without slipping, then derive the equations and then impose the condition when the rolling without slipping is just gets violated. So we'll take that first approach, and then we will go over a second approach. So method 1 is assume rolling without slipping, and then impose impending slip. That is, impose the condition under which it is just about to slip. So if we assume rolling without slipping, so rolling without slipping implies that x is equal to r theta, which means that x dot is equal to r theta dot, which means x double dot is equal to r theta double dot. So we have a relation between x double dot and theta double dot. So we have the friction force F is equal to m times x double dot is r theta double dot. So that's our expression of the friction force. Now keep in mind that in this scenario we cannot assume the friction force to be equal to mu mg, because remember, mu mg is the friction force. It's the limiting friction force. It's the friction force that manifests when there is slipping, or when we are just about to enter slipping. Otherwise, the friction force always remains less than mu mg. So we need to keep that in mind. And here we are assuming rolling without slipping, which means that we are assuming that there is no slipping, which means that we are assuming that this is the friction force and it is less than mu mg. So by assuming rolling without slipping, we are assuming F equals mr theta double dot to be less than mu mg. Okay, mu mg is the limiting friction force at which slipping occurs. Beyond that, the friction force cannot increase anymore. A better expression of this is equal to mu n. I should not just very casually say mu mg, because technically speaking, it should be mu times the normal reaction between the two surfaces that are in contact, and in this case the normal reaction turns out to be mg, and hence we have the mu mg. So therefore, substituting this expression of F into the rotational equation, I have IC theta double dot is equal to T minus mr squared theta double dot. Right? And so that means that the torque is equal to IC plus mr squared theta double dot. By the way, I would like to draw your attention to this term, IC plus mr squared. It is actually the moment of inertia of this disk about the point P, and so which is obtained by parallel axis theorem, and it turns out this way because the equation turns out this way because we are assuming rolling without slipping. If we assume, or if we impose that this wheel is essentially a disk, then IC is half mr squared. So this is going to be half mr squared plus mr squared theta double dot, which is 3 by 2 mr squared theta double dot. So that's the expression for the torque. So from this we can get an expression for theta double dot. So therefore theta double dot as a function of the torque. So as a function of the applied torque, we see that theta double dot is 2t over 3 mr squared. So in other words, if the engine that is causing the motion in this wheel, or the motor, is providing a torque of t, then the acceleration that it produces is given by 2t divided by 3 mr squared. Right? So that is the acceleration of the angular acceleration of the wheel. Now we know that that F is equal to mx double dot and x double dot is r theta double dot. So we can substitute r theta double dot followed by the expression for theta double dot, which is 2t over 3 mr squared. Right? So we cancel m and we cancel one of the r's, and what we get is that the friction force, which is causing the motion of the wheel in the forward direction, is given by 2t divided by 3r. Right after these cancellations. So this is the friction force that the ground is providing. Now here we have throughout assumed that there is no slipping, it's rolling without slipping. Now we made the observation that the slipping occurs when the friction force just exceeds the mu times n or mu times mg value, because that's the maximum friction that the two surfaces that are in contact with each other can withstand without slipping. So therefore, for slipping to just start, F is equal to mu mg. Therefore, slipping just starts when mu mg is equal to 2t divided by 3r. Okay. You could also say that slipping occurs when the friction force 2t divided by 3r is greater than mu mg, greater than or equal to mu mg. Or in other words, when the torque is greater than or equal to 3 mu mg r by 2. So 1.5 mu mg r. So that is the torque if the engine or the motor that is turning this wheel provides a torque greater than 3 mu mg divided by 3 mu mg r divided by 2. That's when we see slipping to be initiated. Now we note that this torque at which slipping occurs is a function of mu, which is the coefficient of friction. And so if mu is low, then then slipping will start at a lower value of torque, and this makes sense. If the surface on which the wheel is moving becomes, or the surface of contact between, or the contact between the wheel and the road, if it becomes more and more slippery, which means that mu becomes lesser and lesser, then the wheel is going to slip at smaller and smaller amounts of torque. And this explains why when you are driving on a slippery road, or when you are transitioning from a normal street to a slippery street, maybe because of icy conditions, then you would have to reduce the torque, reduce or let go the gas pedal so that the torque on the wheels reduce, so that you go below this limit, and then the vehicle gains traction, it no longer slips, and then you have better control on the motion of the vehicle. Alright, so this is method 1, and method 2, we can solve this problem using the second method, where we will assume that there is slipping. Okay, and then we will find out the limiting condition for this slip, again by imposing the fact that slipping happens when the friction force is greater than, or the required friction force is greater than mu mg. The actual friction force between two surfaces can never exceed mu n, in this case mu mg. So when the required friction force to maintain traction exceeds mu n, then we have slipping. We can apply the same idea over here and solve the problem. So here, assume slipping, and impose the fact that slipping occurs when required friction force is greater than mu n is equal to mu mg. Okay, when we say required friction force, we mean the traction force that will prevent slipping. Okay, so in order to formulate the problem in this manner, again let's draw the free body diagram, which remains the same, by the way. Here is our theta, here is our x, this is c, this is the instantaneous point of contact, this is the normal reaction, this is the friction force, and we have the gravitational force. So we know that N is equal to mg. We assume slipping. Therefore, F is equal to mu N is equal to mu mg. Oh, there is a torque here. Our translational equation is mx double dot is equal to F is equal to mu mg, which means that x double dot is equal to mu g. So we have a definite linear acceleration now when the wheel is slipping. The rotational equation is I c theta double dot is equal to T minus Fr. So the same equation, but now we can assume that F is equal to mu mg. So you have T minus mu mgr. Now, because we are assuming slipping, so here x is not equal to theta r, therefore x double dot is not equal to theta double dot r. So we cannot use this relation between x and theta, or x dot and theta dot, or x double dot and theta dot, double dot. However, we note that in this case what is happening is that because there is a torque that is being applied, the internal propulsion mechanism, it has a tendency, remember that slipping can happen in two ways. So slipping one is when x dot is greater than, I should also say therefore x dot is also not equal to theta dot r. Remember that slipping 1 can be when x dot is greater than theta dot r, and slipping 2 can happen x dot is less than theta dot r. Both of these cases slipping can happen because no slip is when x dot is equal to theta dot r. Now this particular scenario, in this particular scenario, this is true. That is, the theta dot is driven. You see, the angular velocity is the variable that is being driven here by the engine or the motor. So the engine or the motor can easily speed up the angular speed, okay, because that is what it is driving. It is only the interaction of the tire with the ground that leads to this angular velocity being converted to a forward going velocity x dot. Okay, so the motive force here, which is the torque, is to produce theta dot, is to produce acceleration, angular acceleration. Now we rely on the traction from the ground to produce a consequent x dot or a x double dot. So because the motive force is causing is actually affecting theta dot, the slipping happens in this case by theta dot r exceeding x dot. So in this case, when it slips due to the motive force being provided by the torque, theta double dot r is greater than x double dot. Okay? So in other words, theta double dot r, which is from this equation, is or from this equation, T minus mu mgr divided by IC times r. This is greater than x double dot, which is mu g. Okay, so this is x double dot. All right. So in other words, T minus mu mgr is greater than IC is half mr squared times mu g and divided by r. So I cancel this r with the one of the r's in the numerator, and what I get is that so T minus mu mgr is greater than half mu mgr, or in other words, T is greater than 1 plus half, so 3 by 2 mu mgr. So you see that therefore slipping occurs for T greater than, and the limiting case is equal to 3 by 2 mu mgr. And you see that this result is now completely consistent with the result that we got in method 1, where what we did is we assumed no slip and then imposed the condition of impending slip, that is when it is just about to slip. And we said that we found that when it is just about to slip, the torque must become greater than or equal to 3 by 2 mu mgr. And here we are saying that if we assume slip, then for that slip to actually occur, the torque must be greater than 3 by 2 mgr. So the two results are consistent. We have applied two methods and we have come up with the same results. Our goal was to determine what motive torque is going to cause the wheel to slip, and the two methods, first being assuming no slip and then imposing impending slip, and the second method being assume slip and find the condition when it is valid. Both these two methods gave consistent results, which shows that the physics that has been used to do the analysis is consistent. It follows the general laws and we are getting consistent results. So this is what I have for this video. Thank you so much.